For more than 50 years, every rocket we've launched with people on it has just gone in circles a few hundred kilometers above our heads, while the last human footprints on the moon have sat there in silence since 1972, and yet suddenly you keep hearing about Artemis, Chinese landings, and a new moon race. So what's actually going on? Is this finally the moment we break out of low Earth orbit again? Or is we're going back to the moon just another line you're being sold? In this video, we're going to pull that promise apart, step by step, and by the end you'll know whether you're really living in the decade humans return to the moon or watching the same dream stall out all over again. The last human footprints on the moon were from an Apollo 17 in December 1972 in a valley called Taurus Littrow. That's the last time anyone went beyond low Earth orbit. Since then, every crewed mission has stayed in a bubble a few hundred kilometers above Earth. No one has gone back to the moon, no one has gone farther out. More than half a century, roughly 2 generations, and our distance record is frozen in time. And remember, the moon is not on the other side of the solar system. On average, it sits about 384,000 kilometers away, around 240,000 miles. At the kind of speed Apollo used, about 39,000 kilometers per hour, roughly 24,000 miles per hour, it's a trip of about 3 days one way. You go there, you stay a bit, you come back, and the whole thing is about a week. In space terms, that is next door. So if it's that close, why did we leave and never come back? The short answer is, the money and the reason for the race both vanished. During the Apollo build-up in the 1960s, the United States was pouring a huge chunk of its federal budget into NASA, peaking at about 4.4% in 1966. That's more than $4 out of every 100 the government spent. Today, NASA's share is around 0.4 to 0.5%, roughly 1/10 of that level. The Cold War beat the other side to the moon, pressure dropped, and so did the appetite to keep spending at Apollo levels. When that happened, crewed exploration shrank down. Instead of building on the lunar foothold, the focus moved to low Earth orbit. First Skylab, then the Space Shuttle, and eventually the International Space Station. The ISS orbits at roughly 400 kilometers, about 250 miles above Earth. That is great for research and technology, but it's still very close to home. You're not traveling to another world, you are just flying laps around this one. So for decades we acted like the moon was finished business. Flags planted, samples collected, TV broadcasts, cut to credits. But here's the question that really matters. While humans stayed away, did the moon just sit there as a static, known object? The answer is no, not even a little. While crewed missions stopped at low Earth orbit, robotic missions quietly turned the moon into one of the best mapped worlds in the solar system. The United States, Europe, India, China, and Japan have all sent orbiters and landers. NASA's Lunar Reconnaissance Orbiter has been circling the moon since 2009, mapping craters and boulders at resolutions down to a couple of meters. You can see individual Apollo hardware sitting on the surface. India's Chandrayaan missions carried instruments to scan minerals and trace water-related signals. China's Chang'e program has landed on both the near side and the far side driven rovers, and even brought samples back from the moon's far side South Pole Aitken region. Japan's Kaguya orbiter, Europe's contributions, all of this stacked up an enormous amount of data. So even though humans haven't been back, our machines have been building a far sharper picture of the moon's terrain, its chemistry, its poles, its interior, and buried in that data was the clue that changes everything. Here's the twist that breaks the old textbook story. The moon is not completely dry, and the little bit of water it has doesn't just sit still. For a long time the standard line was simple. No atmosphere, no liquid water, just dry rock and dust. Apollo samples looked bone dry. Then starting in the late 2000s, instruments on missions like Chandrayaan-1 picked up clear signals of water or hydroxyl groups in the top layer of lunar soil, especially at higher latitudes. That was already surprising. Then came SOFIA, an infrared telescope mounted on an aircraft. In 2020, data from SOFIA gave the first unambiguous detection of actual water molecules in sunlit regions of the moon, not just hydroxyl. After that, scientists used Sophia's observations to build a wide area map of lunar water, published in 2023. That map showed water signatures spread from mid-latitudes down toward the South Pole, with more water on cooler, shadowed slopes and less on surfaces that get cooked by the sun. Put in simple terms, this means the moon has a very thin, very strange kind of water cycle. Individual molecules, or tiny grains of ice and frost, get kicked around by sunlight, by micrometeorites and by the solar wind. They hop, they stick to colder places, they get released from warmer ones, and over time they drift toward the coldest spots. Those coldest spots are the so-called permanently shadowed regions near the poles, crater floors that never see direct sunlight. Temperatures there can hang well below -200 degrees Celsius, below -330 degrees Fahrenheit. At those temperatures, any water or other volatile that lands there basically freezes in place and stays there for geological timescales. You can think of them as natural deep freeze traps. Now, this is not a hidden ocean, is not lakes and rivers. It's mainly water locked in the soil as frost, as ice mixed with dust, as molecules attached to minerals spread across vast areas at low concentrations, plus more consolidated ice in some of those dark craters. You might have to process many tons of regolith to pull out a ton of usable water, but from an engineering point of view, hard to extract is very different from does not exist. And that's where the view of the moon flips from dead rock to active, valuable real estate. So here's the real question now. In a century where energy, fresh water and resources are becoming tighter on Earth, is it still smart to treat a nearby world with water, metals, and constant access to sunlight as a museum piece? Water on the moon isn't just something for scientists to get excited about. Water means drinking supply for crews, oxygen for breathing, and, once you split it into hydrogen and oxygen, high-performance rocket propellant. Combine that with metal-rich rocks you can turn into structures, and polar high ground where you can get almost continuous sunlight for power, and suddenly the moon starts to look less like a destination for a flag and more like a platform. On top of that, there's the strategic side. The moon has line of sight to deep space, radio-quiet regions on the far side for telescopes, and potential positions for navigation and communication infrastructure that support everything else we do beyond Earth orbit. In a world where multiple countries and companies are all pushing outward, the one that builds permanent capability on the nearest world sets a lot of the rules for what comes next. So the old question, can we afford to go back to the moon, is now turning around into something sharper. With everything we now know about lunar water, resources and strategic position, can we really afford not to? But there's a catch that we have to deal with before we talk about the new plans, because the way we went the first time, Apollo, was never built to make staying normal, it was built to win fast. And that leads to the next hard question. Did Apollo actually open the moon, or did it trap us in a one-time stunt that we are only now learning how to move beyond? Here's the harsh truth about Apollo. It looks like the start of a long road, but it was really a sprint that stopped at the finish line. When you zoom out, the numbers are brutal. Across all the Apollo landings, only 12 people ever walked on the moon. Add up every spacewalk, every step outside on the surface, and you get around 80 hours of actual boot-on regolith time. That's less than 4 full days of humans physically exploring another world, total, in all of history so far. Meanwhile, at the peak of the program, the United States was spending the rough equivalent of over $200 billion in today's money to make that happen. All of that money, all of that industrial effort, for an amount of in-person exploration you could fit into one long weekend. So what does that tell you? It tells you Apollo was never designed as a steady, repeatable way of working in deep space. It was a one-off push, tuned to hit a deadline as fast as possible. The mission was simple in terms: land Americans on the moon before the Soviets, bring them back alive and prove whose system could move faster. As soon as that box was ticked, the pressure that justified those insane budgets just evaporated. But if it was so extreme and so short-lived, why couldn't we at least keep the hardware and use it more efficiently? That's where the second part of the story comes in. The Apollo stack, especially the Saturn V rocket, was built for speed, not for a long life. Saturn V was a monster. About 110 meters tall, roughly 360 feet, weighing around 3,000 tons at liftoff. It could throw about 140 tons into low Earth orbit and around 48 tons onto a path to the moon. That is an insane amount of mass to move that far, and it did it with a first stage that produced tens of millions of newtons of thrust, several thousand times the thrust of a big airliner. From a pure engineering point of view, it worked unbelievably well. 13 Saturn V launches, no total launch failures. But here's the catch. Once the goal was met and the last few Apollo missions were cut, the whole production system behind that rocket was shut down. Factories retooled, tooling and jigs were scrapped, blueprints went into archives. The teams of engineers and technicians who knew all the little tricks scattered into other projects, other industries, or retired. Saturn V wasn't something you could just order again later the way you buy another car. The knowledge and the industrial setup that made it possible were allowed to decay. So you had this situation where humanity had a rocket that could fling nearly 50 tons toward the moon in one go, and then, by choice, we walked away from the capacity and didn't replace it for decades. That is not what a sustainable exploration architecture looks like. That is what a one-time stunt looks like. If it was a stunt, did it at least squeeze the maximum science out of those brief visits? Even there you see the same pattern. Science was powerful, but it wasn't the main driver. Apollo brought back about 382 kilograms of lunar samples, around 842 pounds. That rock and soil completely changed how scientists think about the moon's origin. Before Apollo, people were still arguing seriously about three main ideas: that the moon formed alongside Earth, that it was captured later, or that it split off a spinning young Earth. The chemistry and isotopes in those samples pushed everyone toward a different story, a giant impact, where a Mars-sized body hit early Earth and sprayed material into orbit that later clumped into the moon. So scientifically, those missions were gold. They also gave us data on lunar heat flow, seismic activity, surface chemistry, and more. But you have to separate what the science community did with the opportunity from what the system thought it was paying for. In Washington, the message was simple. We planted the flag, we beat the other superpower to the surface, we televised it, we're done. The priority was the visible win, not the long, patient mapping and building stage after it. That's why when budgets tightened, the pieces that survived were the parts you could defend as more directly useful or more modest, not the giant moon program. So what did we do instead of building on that lunar foothold? We turned inward into low Earth orbit, and we stayed there for a very long time. After Apollo, NASA shifted to the space shuttle, a partially reusable system meant to fly often, carry crews and cargo, and make access to orbit more routine. In practice, it never got close to airline-style operations, but it did become the workhorse for building large structures like the International Space Station. Here's the weird thing: the shuttle, station modules, and later vehicles like crew capsules and cargo ships all fly at orbital speeds of about 7 to 8 kilometers per second, roughly 28,000 kilometers per hour, around 17,000 miles per hour, just to stay in low Earth orbit. The moon, orbiting Earth, moves at only about 1 kilometer per second in its path around our planet. In pure physics terms, the step from low Earth orbit to lunar orbit is big, but it's not absurd. We've already done harder things, but psychologically that step might as well have been a jump to another galaxy. For almost half a century, all crewed flights were loops around Earth at a few hundred kilometers altitude. They never committed to the 3-day, 384,000 kilometer jump outward. We built an entire culture of human spaceflight that treats low Earth orbit as the normal boundary, and everything beyond as risky, exotic, special event territory. So after Apollo, you had a mismatch. The technology to go farther existed in principle, but the mindset and the budgets locked us into a narrow shell around Earth. And under all of that, there's one more uncomfortable point. The original moon program never proved we could actually stay there. Apollo did something incredibly hard but also very narrow. It showed that if you build giant expendable rockets and throw enough money and talent at the problem, you can send small teams for short visits, land, explore a small area for a couple of days, leave and abandon almost all of the hardware. It did not show that you can set up ongoing logistics, where cargo and crews flow regularly. It did not show you can reuse your landers or your transfer stages instead of dumping them. It did not show you can live off the local materials, that in situ resource utilization, ISRU, can handle water, air and fuel at scale. It did not demonstrate long-duration habitats dealing with radiation, dust and partial gravity for months at a time. In other words, Apollo proved we could touch and go. It did not prove we could build a permanent industrial-grade presence. The boring stuff you actually need if you want to run a small civilization 384,000 kilometers away. Supply chains, maintenance regimes, power systems, spare parts, local production. None of that was tested on the moon. It was all outside the scope. And that's the key difference this time. When people talk about going back now, they're not just talking about replaying 1969 with nicer cameras. They're talking about solving the parts Apollo skipped, the parts that let you stay, expand, and use the moon as a base for everything that comes after. So the real pressure point becomes this. If Apollo was a brilliant but temporary sprint, what has changed now? What new reasons and new tools make a permanent return feel almost inevitable instead of optional? So here's the blunt question. If we already proved we can touch the moon, why does it suddenly matter so much to go back now? Start with the simplest answer. Water ice changes everything. When Chandrayaan-1 flew around the moon with its moon mineralogy mapper, it picked up clear absorption features that point to hydroxyl and water spread across much of the surface with stronger signals toward the poles. Its radar instrument also hinted at buried ice in permanently shadowed craters. Then Sophia, the airborne infrared telescope, came along and made the first clean detection of actual water molecules in sunlit regions and helped build maps that show water clustering in colder, shadowed spots and near the South Pole. Down in those permanently shadowed regions near the poles, the floors of some craters sit at brutal temperatures, tens of degrees above absolute zero, below about 50 Kelvin, which means colder than minus 220 degrees Celsius, around minus 370 degrees Fahrenheit. At those temperatures, water, carbon dioxide and other volatiles basically freeze and stay put for billions of years. Why do you care? Because water is three things at once. First, it is drinking water for crews. You melt it, you clean it, you drink it. Second, split it into hydrogen and oxygen, and the oxygen becomes breathable air. Third, that same hydrogen and oxygen together make one of the best chemical rocket propellants we know how to use. So if you can pull water out of the lunar soil and ice, you're not just doing science, you're building a local supply of life support and fuel. Think about the logistics difference. Either you lift every litre of water from Earth, through 9.8 meters per second squared of gravity and thick atmosphere, or you use local ice sitting in a crater that never sees sunlight. One path burns insane amounts of fuel and money, the other sets you up to refuel in space. That is why every serious long-term moon plan has polar water underlined in red. But water is only one part of the argument. The moon is also a time capsule. Earth is geologically active. Plates move, mountains rise and erode, crust gets recycled, impacts get erased by weather, volcanism and tectonics. The moon doesn't do much of that. No plate tectonics, no rain, no oceans. Craters that formed more than 4 billion years ago are still there. That means the lunar surface is a record of the early inner solar system, especially the heavy bombardment period that you simply cannot read clearly on Earth anymore. The far-side South Pole Aitken Basin, for example, is one of the largest and oldest impact structures in the whole solar system. Sampling rocks from there and from other ancient basins and deep craters lets you measure how intense the impact rate was, what kind of bodies were hitting, and how the inner planets evolved. That feeds directly into questions like, when did Earth become habitable? When did water and organics arrive? How violent was the early environment for any potential life? You could try to piece that story together from meteorites and from craters on Mars and Mercury, But the moon is close, it is accessible, and we already know from Apollo that the rocks keep good records. Every new core you drill on the moon is basically another data tape from the early solar system. So even if you ignore the fuel, the water, the bases just as a science target, the moon is not done. It is still holding answers we do not have. Now, shift to the part that connects directly to Mars, and to any serious human mission beyond Earth orbit. You might be thinking, why not skip the moon and just go straight for Mars? Here's the problem. The distances and timescales are in a different league. Mars ranges from about 55 million kilometers away at a really close opposition to roughly 400 million kilometers when Earth and Mars are on opposite sides of the Sun. In practical mission design, you are looking at travel times of around 6 to 9 months one way, depending on the trajectory and launch window. That is half a year to almost a year just to get there. Then you probably wait for another good window to come back. The moon, by comparison, is 3 days, not 3 months. 3 days. If you cannot keep humans alive, healthy and productive for a few weeks on the lunar surface with a 3-day emergency ride home, you have no business locking them into a tin can for hundreds of days to Mars, where any serious problem is weeks of delay away from help. So the moon becomes your training ground. Test closed-loop life support there, test radiation shielding there, test how habitats handle dust, temperature, swings and partial gravity there. Shake out your procedures for repairs, medical emergencies and human psychology there. If something fails, you are 3 days from Earth, not half a year. That's the operational argument. There is also a physics trick in play, the gravity well problem. Every time you launch from Earth, you're fighting 9.8 meters per second squared of gravity, plus thick atmosphere that adds drag and heating. You need around 9 to 10 kilometers per second of speed just to reach low Earth orbit, and then more on top of that to head for the moon or Mars. The moon's surface gravity is only about 1.62 meters per second squared, roughly 1/6 of Earth's surface gravity. There is no air, so you don't waste energy ploughing through atmosphere. In velocity terms, getting from the lunar surface up to lunar orbit costs on the order of 2 kilometers per second. Going from lunar orbit onto a transfer path to Mars adds roughly another 1 to 1.5 kilometers per second. So if, and this is the key, if you can manufacture propellant on the moon from local water, and if you can build depots and tankers there, then launching deep space missions from the moon instead of directly from Earth can be much cheaper in total energy per kilogram. Think of Earth as the big, deep well you climb out of once with heavy infrastructure. After that, a lot of your fuel and hardware starts from the smaller well on the moon. That's why people talk about lunar propellant depots, orbital gas stations, and cargo launching from the moon's surface to support Mars missions. Finally, there is the part nobody likes to say out loud, but it drives policy. Whoever gets serious presence on the moon first, especially at the poles and on the far side, gets to shape how space beyond Earth works. The far side of the moon is naturally shielded from most of Earth's radio noise. That makes it a prime site for low-frequency radio telescopes to study the early universe, the dark ages, before the first stars lit up. Put observatories there and you own a unique scientific asset. The near-side and polar orbits also make the moon a useful relay platform. Put communication satellites in lunar orbit or on high ridges, and they can act as hubs for missions going deeper into the solar system or for bases on the surface. You end up with navigation, communication, and observation networks that everything else depends on. And then there is the symbolism and the lore. The first flags next to permanently crewed bases, the first long-term infrastructure, the first resource extraction operations, they are not just about pride. They are about who writes the practical rules, who defines safety zones, how close you are allowed to operate near someone else's site, what counts as fair use of resources. Treaties exist, yes, but the details will be shaped by whoever is actually on the ground. So when you add it all up, water and fuel, unique science, Mars training ground, favourable gravity, and strategic high ground, the question why bother going back to the moon doesn't really hold up anymore. The real question flips to, with all of that on the table, what exactly is the plan? who is racing to get there, and how fast are they moving? Here's the key thing you need to understand now. This is no longer one country casually talking about going back someday. There is an active race underway, with several players, different strategies and real deadlines. Start with the one you hear about the most, NASA and the Artemis program. Artemis is the official US roadmap to get from where we are now, back to the moon, and then on toward Mars. The first big step with people is Artemis 2. That flight is planned as about a 10-day mission, taking 4 astronauts around the moon and back without landing. Launch is currently scheduled for no earlier than March 2026, after a series of delays driven by hardware and test issues. Why does that matter to you? Because Artemis 2 is the moment we finally break the low Earth orbit cage again. It tests deep space life support, navigation and communications with humans on board, at distances farther from Earth than any crew has gone before. If Artemis 2 works, it clears a big psychological and technical barrier that has been in place since Apollo 17. Then comes the mission everyone watches, Artemis 3. That's the first planned crewed landing since 1972, targeting regions near the lunar South Pole. The official messaging now points to a landing around 2028, and even NASA's own leadership admits that date is under serious schedule pressure, because the lander and spacesuits are both complex, behind, and dependent on new technology. The plan is 4 astronauts go to lunar orbit on the Space Launch System and Orion spacecraft. 2 of them transfer to a commercial lander, touch down near the South Pole, spend roughly a week doing surface operations, then ride back up to orbit and home. So the US line in the sand is clear, crew flying around the moon in the second half of this decade, first South Pole landing later in the decade, and a program that keeps going beyond a one-off. Now look at the other main pole in this race, China. China has said very plainly that it aims to land its taikonauts on the moon by 2030. That is not vague talk. They are already flying the hardware pieces that lead up to it. Their Chang'e robotic program has hit a list of milestones Apollo never did, including the first soft landing and rover on the far side, and a sample return from the South Pole Aitken Basin on the far side. Those missions are not just prestige, they're rehearsal for navigation, landing, ascent and sample handling in exactly the kind of terrain future crews will visit. On top of that, China is pushing the idea of an International Lunar Research Station, ILRS, a joint base in the 2030s that starts robotic, then becomes permanently habitable later on. The key point here is not just China wants a base, it's that they want their own legal and governance framework for that base, separate from the US-led Artemis Accords group. That sets up 2 parallel systems of rules on one small world. Now tie in SpaceX, because you can't talk about modern lunar plans without them. NASA picked SpaceX to build the first human landing system, HLS, for Artemis 3. That vehicle is a special variant of Starship, a huge stainless steel spacecraft more than 50 meters tall, designed to take 2 to 4 astronauts from lunar orbit down to the surface and back up. It does not launch fully fueled. The architecture depends on a series of tanker starships launching to low Earth orbit, transferring hundreds of tons of propellant to the HLS vehicle there, and only then sending it onward to the moon. How many tanker flights? Official documentation for SpaceX's bid uses a conservative figure of up to 14 tanker launches, while Elon Musk has talked about more optimistic cases with 4 to 8, depending on payload and how full the tanks need to be. Either way, this is a huge operational challenge. It means the success of a single crewed landing depends on a whole stack of uncrewed launches, rendezvous, and fluid transfers in orbit. If it works, it unlocks a very powerful, fully reusable system. If it doesn't, Artemis has a problem, because right now that's the baseline lander. So you have the US side driven by NASA's mandate, but leaning heavily on a commercial giant to actually touch the surface. But this is not just NASA and SpaceX versus China. There are other serious players filling in crucial parts of the picture. The Artemis program is explicitly international. European Space Agency, JAXA, and Canadian Space Agency are all building critical hardware for the Lunar Gateway, a small space station that will orbit the moon and act as a staging point. ESA is leading the lunar IHAB habitation module, with JAXA providing key life support and thermal control systems, and Canada contributing Canadarm3, a robotic arm for the Gateway stack. Gateway is not just a science platform, it's part of the logistics chain. Whoever routinely docks ships there, moves cargo through it, and uses it as a node for lunar operations is building a long-term presence, not just flying one mission. Then you have national programs that plug in alongside this. ISRO, after Chandrayaan-3's South Pole landing success, has a roadmap that includes a sample return mission, Chandrayaan-4, and a joint ISRO-JAXA mission, LoopX or Chandrayaan-5, to drill and analyze polar ice later in the decade. Japan has already demonstrated high-precision landing with its SLIM spacecraft and is developing a pressurized rover for future Artemis surface activities, so its astronauts can drive around the moon without wearing suits inside the vehicle. And then, underneath the big national flags, you have a layer of private landers and rovers, especially under commercial lunar payload services in the US. NASA is paying companies like Astrobotic, Intuitive Machines, Firefly, and others to deliver instruments and tech demos to the surface, mostly near the South Pole. These missions are not just science. They are testing landing systems, power systems, communication, and prospecting tools, all with the idea that early cargo runs and scouting are done commercially. Some of them have failed or partially failed, which is expected when you're pushing lots of new designs quickly. But the pattern is clear. NASA is trying to make send hardware to the moon a service you can buy, not a one-off government mega project. Put that together and look at what you're really seeing. The US and its partners are building a network, SLS and Orion for crew, Starship HLS for landings, Gateway as the orbiting hub, CLPS landers as the delivery trucks, and long-term plans for surface infrastructure. China is building a parallel chain, Long March rockets, a new crew capsule, a large lander, Farside and Polar Robotic Scouts, and the ILRS concept for a multi-nation base under its leadership. India, Japan, Europe, Canada, and private companies are all adding their own pieces and trying to secure their own roles. This is not a repeat of the 1960s where two superpowers raced to plant one flag. This is a slow, grinding contest over whose hardware becomes standard, whose navigation networks everyone uses, whose base designs get copied, and whose legal language gets treated as the way things are done around the moon. So the real tension now is not just who lands next, it's who manages to turn that landing into a permanent system first, who makes their way of doing things so normal that everyone else has to plug into it. And that sets up the next, harder question you have to look at. If all these players are moving this fast, what kind of new hardware are they actually betting on? And what new technical risks come with these super rockets and mega landers? Here's the part that really changes the game. The hardware we're building now doesn't just replay Apollo, it rewrites what a moon mission even looks like. Start with the size of the machines we're throwing at this. Saturn V, the Apollo rocket, stood about 111 meters tall, roughly 363 feet, with a fully fueled mass around 2.8 to 3.0 million kilograms, over 6 million pounds. Its first stage produced about 34 million newtons of thrust, around 7.6 million pounds force. That was enough to shake buildings and send about 140 tons into low Earth orbit, and around 43 to 48 tons onto a path to the moon. Now compare that to NASA's Space Launch System, SLS Block 1. It's a bit shorter, around 98 meters, about 322 feet, but fueled it tips the scales at roughly 2.6 million kilograms, about 5.75 million pounds. At liftoff, SLS Block 1 produces about 8.8 million pounds of thrust. That's roughly 39 million newtons. Actually, about 15% more thrust than Saturn V, so you've got a slightly lighter rocket, with more push off the pad sending roughly 27 tons toward the moon in its initial configuration. Then you look at SpaceX's Starship with the super heavy booster. Fully fueled, the stack is on the order of 120 meters tall, close to 400 feet, and the combined mass is heading toward 5,000 tons, about 5 million kilograms, once it hits its mature design. The booster alone, with 33 Raptor engines, is already in the ballpark of 16 to 17 million pounds of thrust at liftoff, around 74 to 76 million newtons, more than double Saturn V's thrust. SpaceX's own numbers say Starship is designed to throw up to about 150 tons to low Earth orbit in fully reusable mode, and up to 250 tons if they're willing to expend hardware. So in one generation you've gone from giant disposable moon rocket to government super rocket to fully reusable monster that makes even Saturn V look modest on paper. These things are basically mobile skyscrapers. But the real story isn't just size, it's what we're going to do with them. That's where Artemis 2 comes in. You might think, okay, but it doesn't land, so why should I care? Because Artemis 2 is the deep space shakedown cruise that decides whether the rest of this architecture is even safe to use with humans. Artemis 2 is a roughly 10-day mission. 4 astronauts ride SLS Block 1 and the Orion spacecraft on a free return loop around the moon, then back to Earth. No landing, no gateway, just a flyby. Launch is currently targeted for early March 2026, after a slip from February when a wet dress rehearsal found hydrogen leaks and a valve issue. On that loop, Orion and its crew will travel something like 2.1 million kilometers in total, about 1.3 million miles, and swing out farther from Earth than any humans have ever gone, around 7,500 kilometers, about 4,700 miles beyond the far side of the moon. That's a big jump from Apollo, and from anything we've flown since. The point is simple: you stress test life support, navigation, communication and re-entry systems in real deep space for 10 days with people on board. If those systems can't handle that, they have no business supporting a landing mission that adds a lander, more operations and surface time on top. But even if SLS and Orion work perfectly, they still only get you to lunar orbit. For Artemis 3 and 4, the crazy part is what has to happen next. Starship HLS. Starship HLS is a special variant of Starship built as a lunar lander. It doesn't launch from Earth fully fueled and head straight to the moon. The architecture NASA bought depends on a chain of orbital refueling events. A depot Starship sits in low Earth orbit. Tanker Starships launch over and over, maybe around 10 times based on current NASA and SpaceX planning, and each one pumps hundreds of tons of cryogenic methane and oxygen into that depot. Once the depot is full, it transfers propellant to the HLS Starship, which then finally goes to lunar orbit, meets Orion, picks up astronauts, lands, and later takes them back up. Here's the catch. Nobody has ever done cryogenic propellant transfer at this scale in orbit. SpaceX has done a small on-vehicle methane transfer test and is planning a dedicated orbital Starship propellant transfer demo around 2026, but the full multi-vehicle chain is still in the future. NASA's own documents, plus independent reviews like the US Government Accountability Office and the Aerospace Safety Advisory Panel, point to in-orbit refueling and Raptor engine maturity as a top schedule and technical risks for Artemis 3. If this refueling chain slips, the landing date slips with it. So for the US-led side, the super rocket and megalander story really boils down to this. SLS throws Orion and crew to the moon. Starship HLS has to prove it can safely refuel in orbit and then act as an elevator between lunar orbit and the surface. Both pieces are hard in different ways. On the Chinese side, the hardware plan looks different but the stakes are similar. China's Long March 10, their next-generation crewed launcher, is designed to loft about 70 tons to low Earth orbit and around 27 tons onto a translunar trajectory. It's roughly 90 meters tall, around 295 feet, with a liftoff mass of about 2,187 tons. Their baseline crewed moon mission uses 2 Long March 10 launches, one for the crewed spacecraft, one for the lunar lander. The two vehicles meet up in lunar orbit, dock, move the taikonauts into the lander, go down, do the surface mission, then go back up and rendezvous again to come home. That dual launch architecture is less extreme on refueling, but it's still a serious coordination problem. You need both rockets to work, both payloads to reach the right orbit, and docking and life support to be rock solid that far from home. Long March 10 is basically China's answer to the question, what's your Saturn V or SLS equivalent for the 2030 crewed landing? All of this gets you to orbit and down toward the surface, but the last few kilometers are where the new rules really show up. Apollo targeted equatorial or near-equatorial sites, mostly flat and well lit. The new missions are going after polar regions, especially near the South Pole, where the terrain is rough, crater walls are steep, and lighting is brutal, with long shadows and bright sun just skimming the horizon. You can't just aim visually and hope anymore. Landers now need autonomous hazard detection and avoidance, HDA, and terrain relative navigation, TRN. That means cameras, LiDAR, and other sensors constantly scanning the surface during descent, comparing what they see to preloaded maps, and making real-time decisions about where exactly to touch down. NASA's ALHAT program, Autonomous Landing Hazard Avoidance Technology, has demonstrated LiDAR-based mapping and safe zone picking down to meter-scale precision, and similar ideas are now baked into multiple lander designs. You've already seen this play out. Chandrayaan-3 used a vision-based hazard detection and terrain navigation system to thread its way to a safe site near the lunar South Pole in 2023. Future Artemis landers and commercial landers are pushing for landing ellipses on the order of a few hundred meters or less. Basically, put this building-sized vehicle down inside something like a football field, surrounded by cliffs and permanent shadows, without hitting boulders the size of cars. So the new hardware picture looks like this. Super rockets in the 2,500 to 5,000 ton class, throwing tens of tons toward the moon, mega landers that rely on never-before-proven orbital refueling, and guidance systems that have to land within meters in some of the harshest lighting and terrain you can find on the lunar surface. And here's the tension that builds from all of that. If you're willing to spend this much money, accept this much technical risk, and push landing accuracy this far, what exactly is so valuable at those polar sites that everyone is converging on the same strip of real estate in permanent shadow? Why is everyone suddenly obsessed with the one place on the moon where the sun basically never shows up? At the lunar poles, some crater floors sit so deep and at such a sharp angle that sunlight never reaches them, not for a second in billions of years. These are the permanently shadowed regions, and their temperatures sit around 40 to 60 Kelvin. That's roughly minus 230 to minus 210 degrees Celsius, about minus 382 to minus 346 degrees Fahrenheit. Some spots get even colder, down near minus 233 Celsius, colder than parts of Pluto. At those temperatures, anything volatile that wanders in, water, carbon dioxide, maybe simple organic molecules, basically stops moving. It freezes, it stays, it stacks up over time. The rest of the moon bakes and freezes each lunar day, but these dark pockets are like natural deep freeze vaults, just sitting there, storing whatever they've trapped since the early solar system. So how sure are we that there is actually ice in there, and not just wishful thinking? The first big clues came from missions like Lunar Prospector. It carried a neutron spectrometer that looked for how neutrons bouncing off the surface got slowed down. Hydrogen atoms are very good at slowing neutrons, so if you see a deficit of fast neutrons over a region, that usually means more hydrogen in the soil, which often means water or hydroxyl. Those measurements showed clear hydrogen enhancements at both poles, especially in patches near the South Pole. Later, India's Chandrayaan-1 added more pieces. Its instruments, including the Moon Mineralogy Mapper, saw strong signatures of water or hydroxyl in high-latitude regions, and radar data hinted at materials in some craters that looked like icy, blocky deposits instead of just dry rock. Then you bring in SOFIA, the infrared telescope flying on a 747. In 2020, it nailed down unambiguous water molecules on the sunlit surface, and in 2023, scientists used SOFIA data to assemble a detailed water map from around 60 degrees south, all the way to the moon's south pole. That map showed water clustering on colder, shadowed slopes and surfaces, staying away from the hottest, brightest spots. Put all of this together and the picture is consistent. Hydrogen spikes at the poles, infrared signatures that fit ice or water-bearing minerals, and thermal models saying, "This place is so cold that whatever lands here can survive for billions of years." No single data set is perfect, but they all point at the same thing: real ice mixed into the soil, especially inside those eternally dark craters. Now, here's the part people often get wrong. This is not a hidden lake under the surface, it's much messier. Think of the regolith there as ultra-dry, dusty snow that has some ice grains and coatings mixed in. You scoop up 1 kilogram of that stuff and you might only get tens to maybe a few hundreds of grams of actual water out of it, depending on the site. That means, to get 1 ton of usable water, you might be processing many tons of regolith, maybe tens of tons, over and over, day after day. So mining ice on the moon is more like running a giant dirty chemical plant than cutting blocks out of a glacier. You need excavators or drills that can work at 40 to 60 Kelvin, hardware that doesn't shatter in that cold, systems to heat the soil, drive off the volatiles, capture and purify the vapor, and store the result in tanks. Every molecule you collect has a cost in time, power, and machinery. But if you can do that, the payoff is huge, because water is the most versatile resource you could ask for up there. Take 1 kilogram of water, split it using electrolysis, and you get about 0.11 kilograms of hydrogen and 0.89 kilograms of oxygen. Hydrogen and oxygen, burned together in a rocket engine, are about as good as chemical propellants get. Engines using liquid hydrogen and the liquid oxygen can hit what engineers call a specific impulse of around 450 seconds in a vacuum. In normal language, that means they squeeze a lot of speed out of each kilogram of propellant compared to kerosene-based fuels. So picture the sequence. You dig up icy regolith near the South Pole, you bake out the water, you split it in big tanks, you liquefy the hydrogen and oxygen, and you pump them into storage depots on the surface or in lunar orbit. Then you feed that fuel into cargo tugs and landers. Those vehicles can throw payloads off the moon at speeds of several kilometers per second, up toward escape velocity from the lunar gravity well and onward to high orbits, Earth, Mars, or other deep space targets. You don't have to lift that fuel through Earth's 1G gravity and thick atmosphere. You lift the equipment once, then you let the moon's own ice keep stocking your gas station. That is why everyone is willing to fight the darkness and cold down there. The problem is, we still don't know how patchy or concentrated those deposits really are at the scale that matters for bulldozers and drills. Orbiter maps are great, but they blur over hundreds of meters. For building a base, you care about what is happening meter by meter, trench by trench. That's where the scout rovers come in. Viper was designed exactly for this job, a roughly 500 kilogram rover to crawl around the South Polar region, drill down up to about 1 meter, and directly measure ice content and volatile chemistry in different ice stability regions. It would have carried a neutron spectrometer, an infrared spectrometer, and a drill called Trident to physically sample the subsurface. NASA later decided in 2024 to end Viper's development as costs and schedules slid, and is now looking at other ways, including commercial partnerships, to get similar measurements on the ground. But the mission template is critical. You send a mobile lab into and around the shadowed regions. You drill, you sniff, you map exactly where the ice actually is, how deep it goes, and how dirty or clean it is. Those maps basically tell you where a future base should sit if you want a reliable water supply. On the other major side of the race, China's Chang'e 7 is aiming at the same question. Planned for launch around 2026, it will carry an orbiter, a lander, a rover, and a small hopper probe specifically designed to jump down into permanently shadowed regions near craters like Shackleton and take measurements right inside the cold traps. Chang'e 7 will fly a big suite of instruments focused on water ice detection and surface environment, including cameras, spectrometers, and dedicated analyzers for water molecules. The hopper is particularly important because rolling a rover into a PSR is hard, you can't see anything, and the slopes are brutal. Being able to hop in, measure, and hop out again gives you a way to touch those spots without committing a full-size vehicle to the darkness. So the South Pole story looks like this. a handful of ultra-cold craters, colder than most of the outer solar system, storing ice and other volatiles that could fuel an entire deep space economy, and multiple nations building specialized hardware just to poke, drill, and map those deposits in detail. But here's the catch that keeps the tension high. All of this prospecting is happening in an environment that is actively hostile to human hardware and human bodies, from temperature swings right next door to the poles, to radiation, to dust that eats machinery. So the next question is unavoidable. Even if the ice is there, and even if we can and reach it, can we actually survive long enough on the lunar surface to turn that frozen treasure into something we can use? Here's the part most people underestimate. Getting to the moon is hard, staying alive on it is worse. Start with the basic environment. At the lunar equator, surface temperatures in full daylight climb to around 120 degrees Celsius, roughly 250 degrees Fahrenheit. At night, they drop to well below minus 130 degrees Celsius, around minus 200 Fahrenheit. That's close to a 250 to 300 degree swing every 29.5 Earth days, with almost no atmosphere to smooth it out. So when you think about a habitat, don't think just build a metal box. You're trying to keep people and equipment at something like 20 to 25 degrees Celsius, room temperature, while the ground outside cycles between deep freeze and extreme heat. Structurally, you're putting a fridge inside an oven that slowly turns on then off over a month-long cycle. That means thick insulation, active heating and cooling, lots of radiators and careful orientation, so you're not cooking one side of your base while the other side freezes. Now add radiation on top of that. Earth gives you a magnetosphere and thick atmosphere that soak up most of the high-energy particles flying around the solar system. The moon has neither. It's fully exposed to galactic cosmic rays, which are high-energy particles from outside the solar system, and solar particle events, blasts of protons and heavier ions from the sun during flares and coronal mass ejections. We're not guessing about this anymore. China's Chang'e 4 lander carries the LND dosimeter, which has been measuring radiation on the lunar far side. It found an average dose of about 1,369 microsieverts per day on the surface, roughly 2.6 times higher than what astronauts get on the International Space Station over the same period. And remember, ISS crews are already taking more radiation than people on the ground, even with partial shielding from Earth's magnetic field. Stay unshielded on the moon for long, and your lifetime cancer risk goes up. Your central nervous system takes hits, and a big solar storm can deliver an acute dose that makes you seriously sick or worse. The only real answer is mass between you and space. That means piling meters of regolith over habitats, building berms around modules, or getting underground. This is where the weird geology of the moon starts to look like an asset instead of just scenery. Lunar lava seas you see as dark patches, the Maria, came from ancient volcanic flows. As that lava moved, it would sometimes crust over on top while molten rock kept flowing underneath, carving out tunnels. When the flow stopped and the lava drained, those tunnels could be left behind as hollow lava tubes. We don't have humans inside one yet, but radar from Japan's Selene mission and gravity data from NASA's Grail mission both point to large, intact lava tubes under regions like Marius Hills. Analyses suggest some of these tubes could be hundreds of meters, even up to 1 kilometer wide, and potentially stable. Put a base inside a lava tube and you get a bunch of advantages at once. The rock overhead gives you natural shielding against radiation and micrometeoroids. Temperatures inside should be far more stable, more like a cold cave than a surface that cycles between frying and freezing. You still have to seal and pressurize your internal space and deal with dust and structural safety, but you're not fighting the full brutality of open surface conditions every day. Speaking of dust, this is the part every Apollo astronaut complained about and every future base planner quietly fears: regolith. Lunar soil isn't like beach sand. There's no atmosphere or flowing water to round grains off. Under a microscope, lunar dust particles are jagged, sharp, and often coated in electrostatically charged fine grains. Apollo crews found that dust clung to suits, visors, tools, everything. It got inside the lunar module, irritated their eyes and lungs, and started to wear down seals and joints after just a few days of operations. Think about what that means for long stays. Every time someone comes back through the airlock, they're bringing a little cloud of ultra-fine glass-like dust with them. That dust can clog filters, scratch bearings, jam mechanisms, and cause respiratory issues if it gets into the habitat atmosphere. You're forced to design dust-tolerant joints, external suit ports where suits stay outside, serious filtration systems, and cleaning routines that are more like decontamination than just wiping your boots. Now stack radiation, thermal extremes, and dust together, and you start to see why just landing isn't the victory people think it is. You need to survive there for months, maybe years, while all of this is constantly attacking your gear and your bodies. And your body itself is another problem. On the moon, you don't float, you're in 1/6 G. So if you weigh 90 kilograms on Earth, about 200 pounds, you'd feel like you were only 15 kilograms or so there, around 33 pounds. That sounds fun, long slow jumps, easy lifting. But your bones and muscles are tuned to living at 1 G. In microgravity, like on the ISS, we know you get rapid bone loss, muscle atrophy, fluid shifts, cardiovascular deconditioning. Crews fight that with 2 or more hours of exercise a day and still come home physically weakened. The big unknown is how much of that improves in partial gravity. Like 1/6 G, recent animal studies suggest that 1/6 G helps compared to zero gravity, but doesn't fully prevent bone density loss and other changes. We don't yet have long-term human data. That means the first crews who spend months on the moon are literally running the experiment for the rest of us, testing whether lunar gravity is good enough for long-term health, or whether you still need heavy exercise, artificial gravity solutions, or shorter rotations to avoid serious damage. So if you zoom out, the survival checklist for a lunar base looks like this. You have to manage a temperature range of hundreds of degrees, block radiation levels a few times higher than ISS, keep razor-sharp dust from eating your machines and lungs, and deal with the unknowns of living in 1/6 G for months or years. And yet, despite all of that, multiple countries are still pushing to go, not just for flags or photos, but because the moon isn't just a dangerous campsite, it's also a unique science lab that can answer questions about Earth, the solar system, and the universe that we cannot answer any other way. So the next piece of tension is this. If surviving there is that hard, what kind of science is important enough that people are still willing to take those risks and build those bases anyway? So now you know the moon is hard to live on, the next question is, why are scientists still so desperate to put gear and people back up there? Because the moon is not just a rock, it's a physics and cosmology lab you can't build anywhere else. Start with something very simple that turns into deep physics. The moon is slowly drifting away from us. Thanks to the retroreflectors left by Apollo, we fire lasers from Earth, time the bounce to the picosecond level, and track the distance change. Those measurements show the moon is receding at about 3.8 centimeters per year, roughly 1.5 inches per year. That drift is caused by the tides. Earth's oceans and crust bulge under the moon's gravity. Friction in those tides eats rotational energy from Earth and transfers angular momentum to the moon's orbit. The result, over hundreds of millions of years, the moon moves farther out and Earth's rotation slows down. Geological and fossil data back this up. In the late Precambrian, a day was closer to 21 hours, not 24. The moon's orbit is basically a tidal fossil, a record of how Earth's rotation and oceans have changed over deep time. When you improve those laser ranging measurements and combine them with models of Earth's interior and ocean distribution, you are doing cosmology with solid rock, using a nearby world to read out how our planet has evolved. Now flip around to the far side, the half you never see from Earth, and the science gets even more extreme. The lunar far side is shielded by the bulk of the moon from most of our radio noise, all the FM stations, cell towers, radar, and general electromagnetic trash we spray into space. That makes it the quietest radio place in the inner solar system at low frequencies. Why do you care about low frequencies? Because the cosmic dark ages, The period between the cosmic microwave background and the first stars turning on are best probed by the 21-centimeter hydrogen line, redshifted down to tens of megahertz and below. Those bands are basically impossible from Earth's surface. Our ionosphere blocks or distorts them, and human radio pollution wrecks the rest. Put even a modest dipole antenna array on the far side, and suddenly you can listen to neutral hydrogen filling the universe before the first galaxies formed. Concepts like Farside or the Lunar Crater Radio Telescope talk about thousands to hundreds of thousands of antennas spread over tens to hundreds of square kilometers, built right into the regolith to map that early universe in 3D. That's not just nice astronomy, that's direct data on when the first stars formed, how quickly they heated and ionized the gas around them, and how things like dark matter and early dark energy might have shaped structure. There is literally no backup site for this. If you want clean access to those frequencies, you go to the far side or you don't get them. Then dig under the surface and look at the moon as a seismology target. Apollo planted a small network of seismometers. Those instruments recorded moonquakes and impact events, and what they saw was weird. The moon rings for hours after a hit, because it's dry, fractured, and has no water to damp vibrations the way Earth's crust does. With that tiny network, scientists derive the basic layered structure of the moon. But there are still big uncertainties about its core size, its deep mantle, and how exactly the crust is arranged globally. If you deploy a dense, modern seismic array, dozens to hundreds of stations spread across both near and far side, you can turn the moon into a solved problem. You'd be able to test formation models much more precisely, especially the giant impact scenario and its variants, by seeing exactly how the interior is layered and how dense each layer is. That feeds directly into exoplanet science, because Earth plus big moon systems affect tides, climate stability, and maybe even the chances of complex life. We only know one example in detail, ours. A full seismology map of a broken world like the moon gives you a template for thinking about similar systems around other stars. There's also the thin, almost non-existent atmosphere on the moon, what we call an exosphere. Densities are typically around 10,000 to 100,000 particles per cubic centimetre, compared with roughly 10 billion particles per cubic centimetre at Earth's sea level. That's better vacuum than most lab chambers on Earth. It's a perfect natural lab for studying how atoms and molecules sputter off the surface when hit by solar wind, how they hop along the surface, stick in cold traps, and escape. It's also ideal for watching how dust, electric fields, and plasma interact over long time scales. All of that matters because many bodies in the solar system are airless or nearly airless, from Mercury to most moons to many asteroids. What you learn from watching the lunar surface exosphere system tells you how space weather slowly modifies these worlds, changes their surfaces, and moves volatiles around. Now you might say, okay, but do we really need humans there for this? Some of it, no, robots can do a lot. You can land a small radio array, a few seismometers, and some plasma instruments with no humans on site, but once you push beyond that, you hit practical limits very fast. Building an array of tens of thousands of antennas over hundreds of square kilometers on the far side, routing power and data lines, repairing broken nodes and upgrading electronics as you learn, is much easier with humans setting up and supervising robots locally, instead of piloting everything from Earth with a time delay. The same is true for seismology, drilling tens or hundreds of meters into the crust at multiple sites, handling delicate borehole instruments, and reacting when something gets stuck or breaks. Maintaining cryogenic receivers for ultra-sensitive radio telescopes in the dusty, thermally harsh environment becomes far more realistic when you have trained people on site, not just pre-programmed autonomy. So the bottom line is, the moon lets you read Earth's rotational history in centimeters per year, lets you listen to the universe before the first stars in frequencies you can't touch from Earth, lets you dissect a small differentiated body to test how common Earth-Moon type systems are, and lets you watch how a nearly perfect vacuum interacts with space weather in real time. And all of that high-end science is layered on top of the survival and infrastructure challenges you already saw, which leads to the next pressure point. If you're going to build this level of observatory and lab out there, you're not just talking about rockets and landers anymore. You're talking about full-blown infrastructure, navigation, communication, and even traffic rules around another world. If you want people living and working on the moon, the problem isn't just how do we land them, it's how do we wire up an entire world that's 400,000 kilometers away so it actually functions. Start with the basic communications problem. The moon is about 1.3 light seconds from Earth, one way. That means every signal, even at light speed, takes about 1.3 seconds to get there and 1.3 seconds to come back. Round trip, you're sitting on roughly 2.6 seconds of latency. That sounds small, but it's enough to kill real-time joystick control. If you try to drive a rover from Earth like a remote control car, by the time you see that rock in the video feed and move your hand, the rover has already gone past it or hit it. You have to plan moves in chunks, send commands in sequences, and let the robot handle the split-second decisions locally. It's nothing like Mars, where the delay can be 4 to 24 minutes one way, but it's still in this awkward zone where your brain expects instant feedback and doesn't get it. For live operations, telepresence, repair, docking, all of that feels laggy. So you need smart systems on the moon, and you need really solid links so the delayed control you do have is as clean as possible. Next problem, navigation. Our current GPS and other GNSS constellations were never designed for lunar users. The signals bleed out into cislunar space a bit, and you can sometimes use them in creative ways in high Earth orbit. But you do not get a clean, strong, 4-satellite lock on the far side of the moon. If you want landers and rovers to know exactly where they are, you need a dedicated lunar navigation system. That's why Europe, NASA, and partners are pushing ideas like the Moonlight and LCNS constellations, sets of small satellites in lunar orbit, broadcasting timing and position signals the way GPS, Galileo, and others do for Earth. Each satellite carries a precise atomic clock, broadcasts its time and orbital data, and receivers on landers or rovers can triangulate their position down to meter-scale accuracy, which is critical when your landing ellipse is only a few hundred meters across near cliffs and boulders. With that in place, a lander coming down to the South Pole isn't just guessing, based on onboard IMAS and cameras. It can fuse terrain-relative navigation with GNSS-like beacons to know, within a few meters, I am here on this slope, not on that ridge. Same for rovers. You want detailed maps, you want to mark safe paths, exclusion zones, resource patches. You can't do that accurately if everyone's position has a kilometre of uncertainty. Now layer on surface comms. The polar regions, especially near the South Pole, have a weird geometry. Craters throw deep shadows, ridges catch light at grazing angles, and line of sight to Earth can come and go depending on your exact location. That's bad if you want constant power and constant communication. The trick is to use peaks of eternal light, high spots near the poles that get sunlight almost all the time, to host infrastructure. Those peaks, identified by missions like SMART 1 and later mapping work, are ridges or crater rims that see the sun for the vast majority of the lunar year. Put solar farms up there, and you get nearly continuous power with only short, manageable eclipses. Put communication towers and relay antennas up there, and you create a kind of lunar cell network, line-of-sight links down into bases and mining sites that might be in partial shadow, plus high-gain dishes that talk back to relay satellites and then to Earth. If you design it well, the South Pole starts to look less like a dead zone and more like a very remote Antarctic station, with patchy but reliable connectivity and a central power ridge feeding everything else. Once you have orbital navigation beacons and surface towers, there's another layer you can't dodge: traffic management. Right now, every mission files its own trajectory, works deconfliction with agencies on the ground, and hopes nobody else is trying to land on the same day in the same spot. That breaks quickly once you have multiple countries, multiple companies, dozens of landers and orbiters crisscrossing the same tight set of polar orbits. You're going to need agreed-upon approach corridors, preferred orbital planes, keep-out zones above bases and key science sites, and procedures for what happens if two missions want the same time slot. That starts as coordination meetings and spreadsheets, but it evolves into an actual lunar air traffic control system, even if it's all automated. Someone, or some group, ends up managing who can descend when, how close they can fly over someone else's base, and what emergency rules apply if a lander starts to drift toward a no-go area. Once you have constellations like Moonlight in orbit, relay satellites providing constant links, local cell towers on peaks of eternal light, and a de facto traffic control system coordinating landings and overflights, you've sunk billions into a network that wraps the moon in timing comms and rules. You don't casually walk away from that. Even if one specific program stumbles, the moment a navigation constellation is up, a relay network is routine, and surface towers are online. They become part of the baseline environment everyone expects. Shutting them down would break other missions, including science and commercial ones, and that's painful. So the real shift is this. Once we build a lunar internet, a lunar GPS, and lunar traffic control, the question, are we going back to the moon, quietly changes into who owns and operates the network that keeps the moon running. And that question is a lot harder to roll back. And sitting underneath that is an even more sensitive topic. If we manage to wire up the moon this way, what are we going to do with its resources? Who gets to mine what, and does any of this make economic sense beyond national pride? Why do people keep talking about mining the moon, like it's some instant gold rush, when most of the actual numbers say calm down? Let's start with the one you've probably heard in clickbait headlines, helium-3. You'll hear that helium-3 is this perfect fusion fuel, almost no radioactive waste, tons of it in the lunar soil, just waiting to turn the moon into a giant gas station for Earth. Here's the reality check. Helium-3 is indeed implanted into the regolith by the solar wind, and it's rare on Earth because our atmosphere and magnetic field protect the surface. But on the moon, the concentrations people quote are on the order of parts per billion to, at best in some spots, parts per million. That means if you process 1 billion kilograms of regolith, you're talking about maybe a few hundred to a few thousand kilograms of He3. You're basically strip mining huge areas of the surface to get small amounts of fuel for a fusion technology that does not exist as a working power plant anywhere yet. Fusion reactors that could efficiently burn helium-3 are still in the theory and early experiment stage, not ready to plug into a grid. So yes, helium-3 is real, and it might matter in the far future, but it is not the short-term business model that pays for the first lunar bases. So if not magic fusion dust, what actually is worth chasing in the regolith? The boring answer is the stuff we already know how to use: oxygen, metals, and silicon. Lunar regolith is made largely of silicate minerals and oxides. If you break those down, you find that oxygen locked into those oxides can be up to around 40 to 45% of the regolith by mass. The rocks also carry aluminum, iron, titanium, magnesium, and plenty of silicon. None of that is exotic, but all of it is exactly what you need if you want to build things on site. The key shift is this. Early lunar industry is not about exporting raw materials back to Earth. It's about in situ use. You pull oxygen out of the rocks to breathe and to burn as oxidizer in local rockets. You use iron, aluminum, and titanium to make structural components, tanks, beams, pressure vessel shells. You use silicon and refined oxides to make glass and eventually solar cells. The value is in not having to lift every kilogram of brick, beam, and tank out of the Earth's gravity well. Once your heavy gear is in place, your goal is to stop shipping dumb mass like air, water, and concrete and start making it locally. That leads straight into the idea of turning dirt into building material. Regolith is nasty as dust, but if you handle it right, it's also your main construction resource. One of the most promising approaches people are testing is sintering, heating the regolith with microwaves or focused sunlight or lasers until the grains fuse together into a solid block, without fully melting everything. You can do this in molds or by scanning over the surface. Why does that matter? Because every time a big lander touches down, its rocket plumes kick up dust and gravel at hundreds of meters per second. That spray can sandblast nearby hardware, solar panels, habitats, and even other landers. Apollo already saw this with smaller vehicles and lower landing masses. When you start landing 50-ton class ships near your base, uncontrolled dust becomes a serious threat. If you can 3D print solid landing pads, roads, and protective walls out of local regolith, you turn loose dirt into controlled hard surfaces. You make every future landing safer and reduce long-term damage. So the picture you should have is less picking up shiny rocks, more running a high-temperature bricks and concrete factory with vacuum and robots. But what about shipping things back to Earth? Is that ever worth it? Run through the energy costs. To get off the moon and into low lunar orbit, you need on the order of a couple of kilometers per second of speed. Roughly 2.4 kilometers per second is a good round number. From low lunar orbit back to a trajectory toward Earth, add maybe another 0.8 to 1 kilometer per second. Put simply, leaving the moon is easier than leaving Earth, but it's not free. You still need real rockets, real fuel, and real infrastructure. On top of that, you have to handle re-entry and landing at Earth, and then distribute whatever you brought down. If what you're exporting is just bulk metal or oxygen, forget it, D's. You will never beat Earth-based mining and production on cost for a long time. For exporting to make sense, what comes down the well from the moon has to be extremely valuable per kilogram, like certain isotopes, ultra-pure crystals, or unique optical components that cannot be made as well on Earth. Even then, you'd be competing with advanced Earth-based techniques and later with manufacturing in orbit or at other sites. So the realistic near-term picture is simple. You don't treat the moon as a mine feeding Earth's economy, you treat it as a workshop supporting space operations. Mining, refining, and manufacturing are aimed at feeding local needs in cislunar traffic, not filling cargo ships to ship moon ore back to ground level. That shift in mindset is important. It means the question isn't how many trillions can we dig out of the moon and sell on Earth, it's how quickly can we replace supply ships with local production so bases and depots stop depending on a fragile pipeline from one planet. The moon becomes a staging area, an industrial park for space, not an asteroid-style mine whose output you dump into Earth markets. And once you see it that way, another layer of tension appears. If the moon is more like an off-world factory than a treasure chest, then the real power lies with whoever can afford to build and maintain that factory year after year without running out of money, public support, or patience. Which raises the uncomfortable question you have to face next. Even if the engineering works and the economics add up in this workshop model, can the budgets actually sustain a decades-long push? Or does the whole thing stall again like it did after Apollo? When you ask, are we going back to the moon? What you're really asking without realizing it is, who's willing to pay and who gets to be in charge once we're there? Take the money first, because that drives everything else. NASA's own Inspector General estimates that the Artemis campaign will cost about $93 billion through the end of fiscal year 2025. That's not internet rumor. That's an internal audit that breaks out Space Launch System, Orion, ground systems, Gateway, and more. You're talking about the price of a massive national infrastructure project like a high-speed rail network or a major airport system spread over many years across multiple US states plus international partners, and that's just through 2025. Keeping Artemis going into the 2030s means tens of billions more, no matter how you slice it. So for the US and its partners, going back is not a side quest, it's a long-term budget line that money funds jobs, contracts, local economies, and yes, leverage. Once that many districts and companies are tied into the moon pipeline, they develop a strong interest in making sure the program survives the next election cycle. The same logic applies on the Chinese and Russian side for their own lunar projects, even if the numbers and transparency are different. Now look at the legal side, because that's where the real tension starts to show. The 1967 Outer Space Treaty says no country can claim sovereignty over the moon or any other celestial body. No flags own territory. That sounds clean, but it leaves a giant question open. What about resources you actually dig up? That's where the Artemis Accords come in. They're a set of principles the US and more than 50 partner countries have signed, trying to clarify how you handle things like resource extraction and safety zones around your operations. The language is careful. It says, we respect free access and we're not claiming territory, but we reserve the right to announce zones around our equipment and resource sites to avoid harmful interference. In plain language, that's basically, we're not calling this a land claim, but please don't land your hardware or run your drills inside the area we just spent billions mapping and making safe. It's a way to square real-world operations with a treaty written before anyone thought seriously about lunar mining. China and its partners, led by the China National Space Administration and Roscosmos, are building a different ecosystem around the International Lunar Research Station, ILRS. The ILRS roadmap lays out reconnaissance missions this decade, construction of surface and orbital infrastructure from about 2026 to 2035, and then long-term use after that, with its own governance and cooperation framework. Legal scholars are already pointing out that this effectively sets up a parallel set of rules and habits, a China-centric order around its base, separate from the Artemis Accords bloc. Two partially overlapping, partially competing legal systems on the same small world is not a stable configuration. It's a recipe for friction. That friction, in turn, is a strong incentive for both sides to keep flying crewed missions and building infrastructure, because presence equals leverage. If your astronauts and your robots are sitting on the ground near the South Pole, you're no longer just arguing in UN rooms, you're demonstrating facts on the surface. Then layer in the commercial players. Under NASA's Commercial Lunar Payload Services, CLPS, the agency doesn't build every lander itself. Instead, it buys delivery services from companies, Astrobotic, Intuitive Machines, Firefly, and others. Each contract is worth tens or hundreds of millions to deliver NASA instruments and sometimes commercial payloads to specific regions, mostly near the South Pole. Recent missions from companies like Firefly's Blue Ghost have already shown how this works in practice, with NASA science riding on private landers and investors watching every success or failure closely. That means the moon is quietly getting a supply chain that looks very familiar. Launch providers selling rides, lander companies offering surface delivery, payload customers buying slots, insurers pricing risk, investors betting on who can land reliably. When a lander fails now, it's not just a lost experiment, it's also a financial hit. Share prices dropping, future contracts in doubt. That's a very different dynamic from the Apollo era, where almost everything was national and centralized. All of this feeds back into the rules question. Once private companies are regularly dropping hardware near the same craters, you can't just say, we'll all be reasonable. You need standards for how close you can land to someone else's assets, how you handle plume damage, how you share or protect data about resource deposits, and what counts as responsible versus reckless behavior. Some of that will be written into contracts and bilateral agreements. Some of it will be worked out the hard way, after a lander from one country accidentally damages another's rover or base. And that's the real core of why the question, are we going back, is less about rockets and more about norms. The first countries and coalitions that operate continuously on the moon will, in practice, set the default answers. How wide is a safety zone around a drill site? Is it okay to drive a rover within a kilometre of someone else's lander? Do you have to share certain types of environmental data to protect everyone's equipment, or can you keep it proprietary? How do you handle contamination of a scientifically important site if mining gear sprays dust into it? The law on paper will lag behind what actually happens. In the meantime, whoever is there first with working equipment and permanent crews will be writing the unwritten rules by their actions. Other newcomers will be pushed to copy whatever's already in place, because it's easier to plug into an existing pattern than to fight it. So when you hear Artemis costs $93 billion, or China and Russia are building the ILRS by 2035, don't just think about flags and photo ops. Think about which legal language becomes normal, whose contracts set the standard clauses, whose approach to safety zones and resource rights gets copied. That's the real prize, not just touching the moon, but shaping the operating system that runs it. And once you see that, the next question almost asks itself, if the moon is becoming an industrialized world with its own rules and supply chains, how does that change the way we go to Mars and beyond? Do we treat the moon as a true stepping stone? Or do we end up dragging all of our Earth side with us deeper into the solar system? Here's the big picture you have to keep in your head now. The moon is not the final destination. It's the first rung on the ladder to Mars and beyond. Look at the speed budget, because that's what really decides how hard a mission is. From Earth's surface up to low Earth orbit, you need roughly 9.3 to 10 kilometers per second of speed. That's you fighting 1g gravity and thick air. From low Earth orbit out onto a path toward the moon, translunar injection, you add around 3.2 kilometers per second. So a classic from the ground to a moonbound trajectory stack is well over 12 kilometers per second of total push. Now flip it around and look from the moon's side. From the lunar surface up to lunar orbit, you're talking about something like 1.8 to 2.4 kilometers per second. No atmosphere, 1/6 g gravity. From lunar orbit out onto a transfer path to Mars, depending on the exact trajectory, you might add around 1 to 1.5 kilometers per second. So if you can make propellant on the moon, and you've already paid the cost to put your heavy infrastructure there, you break the problem into two simpler steps. You use Earth's giant rockets to send up machines, habitats, reactors, and construction gear once, and then you let the moon's much smaller gravity well handle a lot of the fuel for deep space missions. That's why people obsess over lunar fuel depots. They're not a side quest, they are how you stop every Mars ship from having to drag all of its fuel out of Earth's gravity well. You refuel closer to the edge of the well, so the total energy you spend per kilogram going to Mars and the outer solar system drop. But fuel isn't the only constraint, and honestly, it's not even the worst one. The hardest part of Mars missions is keeping people alive and functioning for years without resupply. That's closed-loop life support. Right now, even on the ISS, life support is not fully closed. Water and air get recycled, but you still ship up supplies regularly, including food and spare parts. For Mars, that's not good enough. You need systems that can run for months or years with minimal resupply, regenerating air, water, and ideally a big chunk of the food locally. And you can't wait until you're already on a 2-year Mars mission to find out what breaks. The moon gives you a safe but harsh test bed. You can run a base with 4 people for 30, 60, 90 days and force the system to do real recycling. You see which filters clog, which valves fail, how microbes behave in 1/6 g, how your water loop handles trace contaminants, what your food production actually yields over months instead of weeks. If something goes badly wrong, you are a few days from Earth, not half a year. That de-risks Mars massively. You're not simulating in a desert or a lab, you're running the real hardware in a real alien environment. Then there's the biology question we still don't have a solid answer to. How fast does space break the human body, and can partial gravity slow that down enough? In zero gravity, we already know the story. Bone loss, muscle atrophy, fluid shifts, vision changes, cardiovascular deconditioning, all of it shows up. Crews fight it with hours of exercise every day and still come home weakened. On Mars, you'd be at about 0.38 g, on the Moon about 0.16 g. We don't yet know whether those levels are good enough to prevent the worst long-term effects, or whether they just slow them down. Lunar missions let you start measuring that. You can track bone density, muscle mass, heart function, and cognitive performance for crews staying 1 month, 3 months, maybe longer in 1/6 g. You compare that to ISS data. You test different exercise regimes. You see whether certain issues improve or new ones appear. That data feeds straight into Mars mission design. If 1/6 g isn't enough, you start thinking seriously about artificial gravity, spinning habitats, or strict stay time limits. If it is enough, you suddenly have more flexibility for how long you keep people off Earth. Now connect that to the science hardware you're building. We already talked about the farside radio arrays and seismometer networks. If you can build and maintain huge interferometers on the lunar far side, wiring together thousands of antennas over tens or hundreds of square kilometers, you've basically proved you can do large-scale construction and precision deployment in a low-gravity, dusty, remote world. The skills overlap almost one-to-one with what you need deeper in the solar system. Building a radio array on the Moon trains you to build a similar array on Phobos, Deimos, or in orbit around other planets. assembling and maintaining big cryogenic telescopes in lunar shadow trains you for complex observatories in deep space, operating a network of reactors, solar farms and storage systems under constant radiation and dust trains you for power grids on Mars or in the asteroid belt. So the moon starts to look like a full-scale practice arena. You practice logistics chains, you practice emergency response, you practice construction, drilling, mining and manufacturing. You practice keeping a small group of humans alive and sane, with minimal help, in a place that does not care if you live or die. That's the real core idea here. If you can't run a tiny, fragile civilization 400,000 kilometers away, you are not ready to run one 400 million kilometers away. The moon is close enough that you can recover from stupid mistakes, but far enough that you can't fake competence. Mars is where the training wheels come off, and that brings you to the uncomfortable part of the story. Even with all this logic pointing outward, we've already seen one grand push stall out after Apollo. So this time, what could actually stop us? What are the failure modes that can still kill the dream of a permanent human return to the moon? If you want an honest answer about going back to the moon, you have to look straight at the ways it could still fall apart, even now. The first and ugliest one is money. Space doesn't run on inspiration, it runs on budgets. Apollo didn't end because engineers ran out of ideas, it ended because the reason to spend that much vanished. The same thing can happen again. If a big recession hits, or a major war, or some domestic crisis that eats attention and cash. Space programs are one of the easiest big line items to stall. Artemis is already under schedule and cost pressure, China's timelines are ambitious, and every year there are arguments over what should be cut. If national priorities swing hard inward, lunar timelines can slip by 5, 10, 20 years without any new decision being taken. It just quietly stops moving. Then you have the technical nightmare category, the things that might work on paper but still haven't been proven in the real environment. On-orbit cryogenic refueling at the scale Starship needs has never been done. You're talking about transferring hundreds of tons of liquid methane and liquid oxygen between huge tanks in microgravity while keeping them at extremely low temperatures and not boiling off too much. A tiny leak, a valve that sticks, a sensor that lies, and your whole chain of tanker flights fails to fill the depot. Without that working reliably, the entire Starship-based landing architecture stalls, and you have to find a different lander or wait for a redesign. Landing big vehicles repeatedly near fragile infrastructure is another unsolved problem. Apollo landers were relatively small and light, and even they kicked up serious dust and rocks. Now imagine a 40, 50, 60-ton lander coming down near a base with solar panels, habitats, radiators, antennas, and other landers scattered around. The exhaust plumes hit the regolith, accelerate grains to high speed, and you've suddenly got a directed sandblaster pointed at everything you care about. We don't yet have an operational proven method to prevent that at scale, whether that's through pads, berms, different engine configurations, or some combination. If one of the early big landings destroys nearby assets, or worse, damages the very base that crew are living in, it forces a whole rethink. Life support is in this same risk bucket. Closed-loop systems can fail in weird ways, with trace contaminants building up, filters clogging, biofilms forming, or hardware wearing out under partial gravity and lunar dust loads that you didn't fully anticipate. If you lose atmosphere or water recycling on a Mars mission, you're in deep trouble. If you lose it on a moon base, you might limp home, but it would still be a high-visibility disaster. And let's be blunt, a single high-profile fatal accident early in the campaign, especially if it looks tied to risk-taking or cost-cutting, could slow everything down for years. The third failure mode is very specific way, international incidents. Picture this. A lander from one nation comes in a little off target and its plume sandblasts another nation's rover, or damages a science instrument that has been running for years, or even scars the edge of a base. Maybe it's genuinely an accident. Maybe it's rushed engineering. Maybe it's bad planning. From the point of view of the injured party, it doesn't really matter in the moment. There are no police on the moon, No local court, no rapid arbitration panel you can walk into with lawyers. All you have are angry officials on Earth, angry publics, and whatever economic or diplomatic leverage each side can bring. That kind of incident doesn't have to start a war to do damage. It can freeze cooperation, kill joint projects, and push blocs to build separate, redundant infrastructure because they no longer trust sharing. That duplication wastes money and time, which then feeds back into the budget problem, which slows everything down even more. Then there's the quiet killer, public indifference. Right now, Artemis, Starship, China's Chang'e program, Chandrayaan, they all get buzz because Moon is back feels fresh. That can fade fast. If launches turn into background noise, if missions start looking repetitive, if media coverage drifts away, support gets fragile. Space programs are big, long, and expensive. They survive in democracies because voters and taxpayers feel some connection to them. That's why you're going to see a huge push on live streams from the surface, VR experiences that let you stand on the Moon from your living room, education programs, direct Q&A sessions with astronauts from the base. That's not fluff, that's survival. If the next generation grows up thinking people on the Moon is normal and interesting, the line in the budget is safer. If they shrug, lawmakers notice, and the knives come out the next time money is tight. Finally, you have the category everyone loves to mention, and no one can fully plan for, the black swans, the unknown unknowns. Apollo already threw surprises at us. The way lunar dust stuck to everything and tore up seals, the way the Moon rang for hours after impacts, thermal behaviour that didn't quite match expectations, hardware wear that showed up only after repeated cycles in vacuum and dust. None of that was predicted perfectly ahead of time. The next wave will have its own list. Maybe some materials we rely on outgas in hard vacuum and contaminate optical surfaces or life support systems. Maybe regolith chemistry around the poles turns out to be more aggressive than we thought when you heat it, creating unexpected corrosion or toxic byproducts. Maybe long stays in 1/6 G uncover a health issue we've barely seen so far, something with the heart, the brain, or the immune system that only shows up after months. Maybe there are mechanical resonances in huge printed structures that make them fatiguing in ways you don't catch in your FinCAD element models. Any of those could force redesigns measured not in weeks, but in years. New materials, new procedures, new medical protocols, maybe even new mission architectures. So if you put it all together, the dream of going back can still be killed by budget gravity, by technical failures in refueling, landing, or life support, by diplomatic accidents in slow motion, by the public losing interest, or by nasty surprises in lunar physics, chemistry, or biology. None of those are hypothetical in the abstract, they all have real concrete ways they could show up. And yet, knowing all of that, the major space powers are still pushing ahead, arguing that the benefits and the strategic risks of not going are bigger than the dangers of trying. Which leads to the part you actually care about in your own life. Assuming we push through all of this and build a real lunar presence, how does that change anything for you sitting on Earth? You've heard all the big picture talk about Mars, bases, but there's a simpler question you actually care about. If humans live on the Moon again, how does that change your day-to-day life on Earth? First angle, hardware. Apollo didn't just give us nice black and white footage, it forced a leap in integrated circuits, materials, and systems engineering that fed into the electronics you're using right now. The Artemis era is doing the same kind of forcing function, but pointed at problems you'll feel directly. To keep people alive on the Moon, you need power systems that are brutally efficient and reliable. That pushes high-efficiency solar cells that work after being hit with radiation and dust, and lightweight batteries that can cycle over and over in wild temperatures. Those designs don't stay stuck on the Moon. Manufacturers will reuse the same cell chemistry, panel designs, and power electronics in things like rooftop solar, grid-scale storage, and emergency systems on Earth. When you see cheaper, more rugged panels and batteries show up in rural villages, off-grid cabins, or disaster relief kits, a lot of that will trace back to, we built this for a lunar night, and then realized it works great in a hurricane zone. Same story with materials. Lightweight composites that can handle vacuum, radiation, and mechanical fatigue without constant maintenance are exactly what you want for aircraft, cars, wind turbine blades, and building components. The pressure to shave every kilogram off a lunar habitat or rover pushes companies to invent new alloys, new 3D printed structures, new coatings that resist abrasion and dust. Once those exist, they are going to be used in regular construction vehicles and infrastructure because lighter and tougher always wins. Then there's closed-loop water and waste systems. On the moon, every litre of water is precious. You're forced to reclaim humidity from the air, recycle urine and grey water, and squeeze every bit of usefulness out of waste because resupply is rare and expensive. The same hardware, scaled and simplified, is exactly what dense cities and disaster zones need. Systems that can clean and reuse water on site instead of relying entirely on huge centralized plants and long pipes. So the tech that keeps a crew of 4 alive in a habitat at minus 150 degrees Celsius outside also shows up later as compact water units in places with drought, flooding, or broken infrastructure. Second angle, launch cost. If fully reusable heavy-lift vehicles like Starship get anywhere close to their target performance, putting a kilogram into low Earth orbit drops from only governments and huge corporations can afford this to serious companies, universities, and even small countries can play. You're going from tens of thousands of dollars per kilogram toward numbers that look more like shipping a container across an ocean, maybe a few $100s per kilogram in the optimistic scenarios, even if reality lands higher. What does that actually change for you? It means you get denser climate monitoring constellations watching greenhouse gases, ice, storms and oceans in much finer detail, because launching hundreds or thousands of small satellites becomes affordable. It means global broadband becomes genuinely global, including remote areas that today barely have 3G coverage, because internet constellations can refresh and expand faster. It means more Earth observation startups, more space-based disaster warning systems, more competition on data and connectivity. In short, the same rockets that lift lunar landers will also quietly upgrade your weather forecast, your internet access, and the data we have about the planet you're standing on. Third angle, psychology. For a kid born now, it's entirely possible that by the time they're in school, humans have been living on the moon continuously for their entire life. The same way the ISS has always been there for today's kids. Growing up in a world where there are people on the moon right now is just background noise changes what feels possible. If that's normal to you, then projects that sound wild today, global carbon capture, continent-scale energy grids, serious asteroid deflection plans, don't feel like science fiction. They feel like things adults do when they decide to solve a problem. A continuous human presence off-world lifts the ceiling in people's heads. More students aim for engineering, medicine, physics, robotics, not because of one big flag moment, but because the whole environment keeps telling them building crazy, hard things is something we actually do. There's also a cultural shift around risk that comes with this. Real lunar operations won't look like clean, safe sci-fi. There will be accidents, injuries, close calls, and maybe tragedies. If the public sticks with it, they're going to have to relearn that exploration and technology at the edge always carry risk, and that zero risk is not a real option. That matters for things that have nothing to do with space. Understanding probability, trade-offs, and long-term bets is exactly what you need when you're voting on climate policies, pandemic responses, AI regulation, and infrastructure. If a society gets used to watching crews accept real, visible risk for long-term goals, it gets a little easier for that same society to accept hard choices and delayed payoffs on Earth. If it can't, then both space and Earth projects get strangled by never fail, never hurt anyone, never take a chance thinking. And finally, there's the perspective piece. Astronauts who've seen Earth from 400 kilometers up talk about the overview effect, that gut-level shift when you see the whole planet in one shot, thin atmosphere. Now imagine seeing Earth routinely from 400,000 kilometers away, a small blue sphere you can cover with your thumb at arm's length, with instruments sharp enough to show city lights and weather systems in insane detail, and doing that not once as a stunt, but over and over with more people experiencing it. Those images and live feeds will be everywhere. Classroom walls, news segments, VR tours. It's harder to pretend that your country is the whole story when you can literally see the entire planet as one glowing object in the sky. It's harder to act like the next election is the only timescale that matters when you're building hardware expected to survive lunar nights and keep running for decades. Even centuries start to feel like short-term patterns on top of a much bigger shared background. So yes, a lunar return changes spaceflight, but it also creeps into your power grid, your water systems, your internet, your education, your sense of risk, and your sense of where you live in the universe. And once you've tied all of that together, technology, economics, survival, psychology, you finally get back to the question we started with. Knowing the benefits, knowing the risks, knowing who's racing and what's at stake. Can you actually give a straight answer to, are we really going back to the moon? And will we stay this time, or is this just Apollo all over again with better cameras? So are we actually going back to the moon? Or is this just another round of PowerPoints and hype that fades out in a few years? On paper, the answer is yes, and not just once. Artemis 2, 3, 4 are not vague ideas. They're funded programs with hardware in various stages of testing and assembly. China's 2030 crewed landing goal isn't just a slogan. It sits on top of a whole Chang'e robotic campaign that's already landed and returned samples. The International Lunar Research Station plan has roadmaps, partner talks, and precursor missions lined up. Private landers and orbiters are already flying under programs like CLPS, some failing, some succeeding, but all adding real data and experience. This is not the situation right after Apollo, where the line quietly went flat. There are multiple independent pipelines of missions from different countries and companies all pointing at the same small world. The more honest answer, though, is that the dates are the only part you should treat as soft. NASA's own Inspector General has called the current Artemis schedule unrealistic. You can see why. New super rockets, new spacecraft, new landers, new refueling methods, new suits, new habitats, all in one decade. That's aggressive even by optimistic standards. China's 2030 target for taikonauts on the moon has slack built in, but they still have to finish Long March 10, the new crew vehicle, the lander, and the whole dual launch architecture. So if you're asking, will Artemis 2 fly exactly when they say now? Or will the first South Pole landing happen in year X? The smart bet is no, some of those dates will slip. Rockets will scrub on the pad. Landers will need redesigns after test failures. Life support hardware will throw unexpected issues in long-duration tests. Budgets will wobble. That's normal. The key thing is the direction of travel, and that part is not subtle. Technologically, everything is pointed outward, back toward the moon and then beyond. The deeper reason it's hard to walk this back now is capability. We're past a point of no return in terms of what humans know how to do. Reusable boosters are no longer theory. They're landing, flying again, and dropping launch prices. Autonomous precision landing is being proven by multiple missions near the poles. Orbital rendezvous and docking are routine. In situ resource utilization is still early, but the basic chemistry and process steps are understood. Even if Artemis as a specific program collapsed, that knowledge would still exist in design teams, in companies, in open literature. Someone else, another agency, another nation, a coalition, a consortium, could pick it up and spin a different flag and logo around it. Compare that to the 1970s. Back then, almost all the critical expertise and tooling for Saturn V and Apollo lived inside a narrow slice of the US aerospace ecosystem. Shut down that pipeline and large chunks of the know-how decayed with it. Today you have the US, China, Europe, India, Japan, private launch companies and more, all iterating in parallel. You'd have to convince a lot of independent actors to all stop at once for a long time to really kill the capability. That's unlikely. So the practical question isn't do we touch the moon again with humans, because that's basically locked in. The practical question is, what does that contact look like over time? If all we do is a few headline landings, a handful of missions that plant flags, shoot 8K video, collect samples and then go home, we've basically done Apollo with nicer cameras. That would be a rerun. Impressive, yes. Inspiring, probably. But structurally the same story. A sprint, a spike in attention and spending, and then a long flat line. The more serious version of going back looks very different. It's not about whether we land, it's about whether we stay. Staying means there are always people, or at least always active assets on or around the moon. It means habitats that run year after year, with crews rotating through. It means industrial zones that actually produce useful things, oxygen, fuel, 3D printed structures, maybe specialized electronics or optics later. It means scientific stations that outlive any one program manager or president. You measure staying in boring ways. How many consecutive years has someone had boots on the ground or ready to occupy bases? How many resupply and crew cycles have happened without huge gaps? How much local production has replaced shipments from Earth? How many missions genuinely depend on lunar propellant, lunar infrastructure, or lunar labs, such that you can't just shut them off without breaking a bigger chain? If, 10 or 15 years from now, the moon has a small but continuous human presence, with cargo landers coming and going, with a navigation and comms network everyone uses, with bases that have layers of upgrades and extensions bolted onto their original cores, then the answer to "are we really going back?" becomes almost too small. At that point, the moon is simply up there, occupied, part of our normal operating space. If instead we get a burst of activity and then another long quiet period, you'll know we treated it as a selfie stop, a place to prove we could still do the hardest thing in the neighbourhood and then retreat. So where does that leave you? Right now, watching all this from Earth. The honest closing is this. Yes, you are living in the decade humans return to the moon. That part is essentially baked in. The only real unknown is what story we write with that return. Do we treat the moon like a backdrop for a few more historic photos? Or is the moment we finally admit we're a species built to live on more than one world and start acting like it, even when it's hard, slow and messy? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.